in which we have applying the biasing voltage VCC over here. Applying the biasing voltage VCC over here, and with that we have the resistances, which is R1 over here, R2 over here, then we have RC over here, and then we have RE over here, which is representing the emitter resistance, the collector resistance, and then we have R1 and R2. They are being connected to basically the base of the transistor. With that, we have also the input signal, which is being applied through capacitor C1, and then we are taking the output signal through the collector of the transistor via capacitor C2, and over here we have the output which is going to be taken from this. Now, as you know, we are doing the DC analysis of the circuits. So this means that for DC analysis, the capacitor C1 and C2, they will be taken off. And once they are going to be taken off, what we are left with, we are left with circuit which is something like this. Are you with me? Can you see it
Yes,
clear?
sir.
Okay.
Yes, sir.
Okay. So this is now the circuit which is left with us. Now, as you can see, this specific circuit can be solved with two ways. One is called the exact method. The other one is called the approximate method. Okay. So in the exact method, how we are going to proceed, let's see. Everybody knows about Thevenin Theorem, which you have studied in your basic electrical engineering course.
Yes, sir.
Okay, so if you see, again, what we can do, we can simplify this circuit. And if we simplify this circuit, so for the simplified circuit, we can say that we have we have the transistor and we have the collector. The collector is having the resistance RC, and this is being connected to the VCC, which is the biasing source. As well as we have a resistor R1 and we have a resistor R2. They are being connected to the base of the transistor, and with that, to the resistor R1 we have the VCC, which is the biasing source, which is being connected to the one side of R1, right? And then the R2 is being grounded, as well as RE, which is also being connected to the ground. Is this thing fine? Are you with me up till now?
सर
Yes,
ये
sir.
R1 R2 ये पैरेलल में सीरीज में लगे हैं.
अगर आप देखें, if you see in this circuit, I haven't changed anything up till now.
Yes sir, clear.
ठीक है जी. I haven't changed anything up till now. I have just made it a simplified one. Right? Are you with me now?
Yes, sir.
So what I have done, I have just simplified it, and with the simplification, now I can actually say R1 is connected to the base, as well as the other end of the R1 is connected to VCC. R2 is one end of the R2 is connected to the base, and the other end is connected to the ground, right? ठीक है जी. Now when looking at the base, what we can say, we from this end, we want to see that what is going to be the Thevenin equivalent of this circuit when looking from the base of the transistor. Are you with me? When
Yes, sir.
looking from this side, what is going to be the equivalent circuit which we can have from this combination of R1, R2 and VCC, right? So when looking from this side, we can actually make the Thevenin equivalent of this circuit. And how we can do that? That if you see, to find the Thevenin voltage and to find the Thevenin resistance. So let's suppose we start with to find the Thevenin resistance, which in our case we call this Thevenin resistance as RTH, right? RTH is going to be the Thevenin equivalent resistance. And how we can find this? The starting point is to find this, what we need to do, we need to have whatever the biasing source which is being connected inside this circuit, that is going to be short circuited, right? So if we are going to short circuit this VCC, so what we are left with, if you see, let me just redraw it. So when I redraw it, so what we are going to have, we have R1 and we have R2, right? And looking from this side, this we call it RTH, right? Now the other end of R1 is going to be grounded, because what we have done, we have short circuited the whatever the voltage source which was connected in the circuit, and then the second end of R2 is also grounded. So from looking from this side, the RTH should be equal to anybody?
R1
R1
plus
plus.
R2.
R1 plus R2, are you sure?
Yes, sir. सीरीज
सर
में
ये
लगे हैं ना, तो
अगर सर्किट ग्राउंडिंग है तो फिर तो ठीक है, R1 लगा.
आप देखें हम कहां से देख रहे हैं इसको. We are looking
तो
from
फिर
R2.
we are
Sir,
looking
G
from
R1 R1 dot R2 divided by R1 plus R2.
so this means R1 and R2, they are in parallel, right?
Yes, sir.
Because this point is actually the base of the transistor, right? And when we are looking from this side, so this means R1 and R2, they are now in parallel. Are you with me?
Yes, sir.
बात
yes
समझ
sir,
में आ रही है?
yes sir, yes sir.
Right? So what we can say, that the Thevenin equivalent resistance RTH should be equal to R1 in parallel to R2, right? And similarly, if I want to find the Thevenin equivalent voltage from the same side, so what I need to do, I need to reinstall the voltage source which was there. And if I'm going to reinstall the voltage source, So it is going to be, what we can say, this is R1, this is R2, and we have VCC, which is again going to be connected inside the circuit. And looking from this side, what is going to be the Thevenin equivalent voltage, which we say ETH, right? So to figure it out this, what we can do, how we can find ETH? Anyone?
Voltage divider.
So if we use the voltage divider rule, right? So in that specific case, what we can see that ETH should be equal to the drop across the R2 resistor. Are you with me?
Yes, sir.
Right? And drop across R2 resistance, we can call it VR2, right? The drop across this resistor, which is, we call it VR2, right? So VR2 should be equal to the Thevenin equivalent voltage, and this VR2 can be calculated as, what should be the value of VR2? Anybody?
Sir, VCC
VCC into R2 divided by
into
R2 parallel R.
Now
सर ये
it's
तो पैरेलल में कनेक्ट है दोनों ना, वोल्टेज सेम नहीं होगा
जी,
सर, ये दोनों रजिस्टर तो एक दूसरे के पैरेलल में कनेक्ट है ना।
अब आप देखें यहाँ पे पैरेलल है कि सीरीज है?
सर बेस के साथ कनेक्ट नहीं है ट्रांजिस्टर के।
हम क्योंकि देख कहां से रहे हैं, हम देख रहे हैं इस पॉइंट से।
पहले भी सर जी इधर से ही देख रहे हैं।
जी पहले भी इधर से ही देख रहे थे, लेकिन वहां पे जो है R1 जो था, हमने क्या किया था, इफ यू टेक अ लुक, R1 हमने क्या कर दिया था, शॉर्ट कर दिया था। ठीक है जी, आर
यस
यू विद
सर।
मी? ठीक है, नाउ हम देख यहां से रहे हैं, लेकिन यहाँ पे क्या बन रहा है, यहाँ पे आप देखें तो ये क्या बनेगा, केवीएल बनेगा ना इस लूप में।
यस सर।
जब इस लूप में केवीएल बनेगा तो ये लूप क्या आ रहा है, सीरीज में आ रहा है।
यस सर।
ठीक है जी, जब सीरीज में आ रहा है तो आप इसको सीरीज में लेते जाएं कि VR2 should be equal to the current which is flowing in the loop into R2. Are you with me?
यस सर।
And the current flowing over here, we say it is I, right? If I say the current flowing over here is I, right? Are you with me?
यस सर।
So ETH should be equal to VR2, where VR2 is equal to the current which is flowing inside the loop into R2. And what is the current flowing inside the loop? What is I equal to?
VCC divided by R1 plus R2।
Right? So this means I should be equal to VCC divided by R1 plus R2, right? So what we can say, ETH should be equal to VCC divided by R1 plus R2 into R2. That is our ETH. Are you with me?
Yes, sir.
ठीक है जी. So what we have achieved from this, we have actually achieved the equivalent circuit for R1 and R2, right? And once we have achieved this, we can replace this inside our circuit, which is this one, right? So we can replace this with our values, and when we replace this with our values, so what we have now, we have RTH, which is now connected to the base of the transistor. Then we have RE, or here we have RC. RC is connected to VCC, and over here we have ETH, which is being connected over here, right? Now the circuit has become very simplified. Are you with me? So this means the current flowing over here is IB, the current flowing over here is IE, and the current flowing over here is IC. Are you with me?
Yes, sir.
So this means we can have the input side as well as we can have the output side. Now at the input side, what we have this is our input side, right? So applying KVL to the input side, this means we can have this is our loop. So applying KVL to the input side, we can have the, if you see, applying KVL to input of the circuit. So this means we have ETH is equal to the drop across RTH, which is IB into RTH, plus the drop across the base emitter junction, which is VBE, right? So plus VBE, and plus the drop across the emitter resistance, which is IE into RE. Are you with me?
सर आपकी
Yes,
आवाज
sir.
कट रही है
Yes, sir. Yes.
नहीं ठीक ठाक आ रही है, आपकी सिग्नल का मसला होगा.
तो देख लें, ठीक है जी. So again, let me just repeat it if somebody has missed it. So what we can say that we can apply KVL to the input side, and when we apply the KVL to the input side, so we can write ETH is equal to IB into RTH, where IB into RTH is this drop, right? IB into RTH is this drop. Then we have the drop in the base emitter junction, which is VBE, and then we have a drop across the RE resistance, which is RE into IE. And what we have done, we have written this, the equation over here. Are you with me?
Yes, sir.
Right?
Yes, sir.
And we also know from our previous knowledge that if we want to simplify this equation, so from our previous knowledge we know this thing, that IE is equal to beta plus 1 times IB. Everybody is fine with this?
Yes,
Yes,
sir.
sir.
And what we can do, we can replace the IE in the equation with IB. So what we are going to get, ETH is equal to IB into RTH plus beta plus 1 times RE and plus VBE. Are you with me? Right?
Yes.
Yes, sir.
And from here we can find the value of IB, and IB can be written as IB is equal to ETH minus VBE divided by RTH plus beta plus 1 times RE. Right? Are you with me?
Yes.
Right? So if you see, in this way, if you have a voltage divider circuit and if you go with the exact method, we will have the equation which is more or less similar to the biased emitter circuit, with only difference that we have in the numerator, or there we have VCC, which was the biasing voltage. It is being replaced with the Thevenin equivalent voltage, and in the denominator where we had the base resistance, it is being replaced with the Thevenin equivalent resistance, right? And the rest of the equation IB is similar to the equation which we have obtained in emitter biased configuration circuit, right? Are you with me?
यस सर इसका फायदा क्या है थेवेनिन रेजिस्टेंस और थेवेनिन वोल्टेज उसकी जगह पर फाइंड करने का?
ओके जी, अगर आप देखें तो initially what I have said, the voltage divider circuits, they have more stability as compared to if we do not have the emitter resistance in the circuit. So if you see that once we were doing the first circuit, which was the
बेस कॉन्फ़िगरेशन हो रहा था बायस्ड बेस.
yes the fixed bias configuration circuit. So in that, if you see, we do not have any resistance in the emitter leg, right? And once we do not have any resistance in the emitter leg, so if the beta changes, right? So if the beta changes, there is a direct impact of the variation in the collector current, right? And
यस सर
are you getting my point? So if
यस
beta
सर वो
changes,
एग्जांपल हमने
जी इसीलिए वो एग्जांपल मैंने आपको असाइनमेंट में दी थी. So if the beta changes, the collector current have a big variation with the variation of beta, right? But once we have something in the denominator of the base current in terms of beta, so when the beta changes, so this means there is something which is countering the numerator beta with the denominator beta, right? And in this way, if there is a change in beta, so the overall impact of change is very, very small as compared to change when there is no beta in the denominator, right? So due to that
Yes,
reason,
sir.
these circuits, when we have an emitter resistance in the circuit, they are more stable as compared to the fixed biased configuration circuits. Are you with me?
यस सर
Yes, sir.
बात समझ में आई है आपको?
Yes, sir.
Okay, so if you see, if I'm going to write the equation on the output side, So again, this is the circuit, right? And for the output side, the equation will be, we will have this as the output side, right? And the output side, applying KVL over here to the output side. So we have VCC at the top, then we have a drop in the collector resistance, then we have a drop in the VCE, which is the collector emitter, and then we have a drop in the emitter resistance, right? So applying KVL to the output side, what we are going to get, KVL to output side. So what we are going to have, we will have VCC, which is equal to ICRC plus VCE plus IERE, right? And we also know this thing that IE is approximately equal to IC, as the value of IB is very small. So what we can say that VCC is equal to ICRC plus RE plus VCE, right? Or this means what we can say that VCE is equal to VCC minus ICRC plus R, right? And the rest of the thing is the same what we have done in the previous emitter bias configuration circuit, that it is going to provide us the two extreme points. One is the IC maximum, which is going to be in the saturation region when we put VC equal to 0. When we put VC equal to 0, so this means IC maximum or IC saturation will be actually equal to IC is equal to VCC divided by RC plus RE. Are you with me? And similarly, if you put IC equal to 0, VCE is equal to VCC. And this means it is going to provide the two ends of the DC load line, right? And from there, we can also know how we can find the Q point in the specific circuit. Are you with me?
Yes, sir. Yes.
Yes, sir. Yes, sir.
ठीक है जी. Now this is basically the exact method, right? So in the exact method, we try to go with the Thevenin equivalent circuit. The other method is called the approximate method, right? In the approximate method, what strategy we are going to use? We will be using the strategy, okay. The second method is called the approximate method, right? In the approximate method, what we say that we have basically R1 and we have R2, right? And R1 and R2, if you see, they are being connected to the base, right? And at the base, we have basically something, then we go into the emitter leg, right? And in the emitter leg, we have the emitter resistance, RE. Are you with me?
Yes, sir.
We also know this thing that from the equation, we also know this thing that IE is equal to beta plus 1 times IB, right? IE is actually equal to beta plus 1 times.
Mike Malika.
Are you with me?
Yes, sir.
Okay. And now if we say that if the current flowing in R1 is, let's suppose we say the current flowing in R1 is I1, right? Now at this specific point, the current will be split into the base current IB, as well as there will be some other current I2 which will be flowing in R2. Are you with me?
Yes.
Now if we say that I1 is equal to IB plus I2 from this circuit. Are you with me?
Yes.
Right. But as we know that the value of IB is very, very small, right? So if the value of IB is very, very small, so what we can say that I1 is approximately equal to I2, right? Are you with me?
Yes, sir.
If the base current is very, very
Yes, sir.
small and it is negligible as compared to I1 and I2, so what we can say I1 is approximately equal to I2, right? And if this is the case, so what we say that the value, this means no current is actually flowing over here in the base of the transistor, right? So whatever the current I1 is flowing in R1, so this means almost the current value of I2 is actually equal to I1. So this means the current flowing over here in the base is negligible as compared to the current I1 and I2, right?
Yes, sir.
So due to this reason, what we say that the resistance which is being offered to the base current is very, very high,
Yes, sir.
right? Are you getting my point?
Yes, sir.
Therefore, the current which is flowing in the base is very, very negligible as compared to the current I1 and I2.